So we're talking about rate law for the first time in this course, but we did talk about it last year a little bit. And rate law is tied to the rate of reactions. Okay, how fast a reaction goes. And because we're talking about the speed of which a reaction goes, it's usually measured in molarity per time period. So you'll see concentrations, okay, over some change in time or seconds. So molarity per second is one way we like to measure that. But you'll see some designations where you'll see the change of some reactant X. Okay, you'll see that change over the change of time. Okay, and for those that are learning about derivatives, you can see where we can start studying derivatives in about an instantaneous change, okay, a point of a slope there. But we'll get to all of that at some point, but not today. So what I want to talk about is that we're talking about the speed of reactions now. How fast? Rate law is tied to essentially how fast will a reaction go. And what I want to say today is everything we've learned about equilibrium and thermodynamics essentially is tied to this. However, the biggest misnomer, the biggest mistake people make is they think delta G somehow is equal to the rate. And I have to nip this in the bud, and it is not. Although delta G is tied to the second law of thermodynamics, and it gives us direction in a reaction. Okay, if there's a directionality in a process, delta G does not tell me how fast a reaction will go. So delta G may be very, very spontaneous, meaning very negative. But a negative delta G means that there is a what? Only a pathway for the reaction to go and increase the entropy of the universe. It doesn't tell me how fast. Case in point, we know that the reaction between oxygen and, let's say, gasoline, octane, is very, very spontaneous. It can burn, it can explode. Reaction goes forward. We never see CO2 and water recombining to make gasoline and oxygen. So we know that oxygen and gasoline combusting into CO2 and water is very spontaneous. But how fast it occurs has nothing to do about its delta G. For instance, you have gasoline sitting in our cars outside in the parking lot, and there's oxygen in the tank. Can't help but not to have oxygen in the tank. As you use up the gasoline, air from the outside goes into the tank. It's not a vacuum. So you've got oxygen and gasoline sitting there, but the reaction isn't going. Okay? But delta G is negative. So how fast the reaction goes has nothing to do with the value of delta G. Okay? So if something is spontaneous, get it out of your head, the reaction goes fast. They will attack you on that principle. Delta G is a pathway. It means when the conditions are set, the forward direction, if it's negative, can occur. Okay, so spontaneity means it can occur with the right set of conditions. Now, what are those conditions? Well, the reactants have to be in a state which they can collide, okay? Or they need some what? Activation energy to make their reaction start. These are the conditions by which delta G doesn't speak to. It just says the process is spontaneous. It doesn't speak to all the other conditions. So things can be very, very spontaneous, but the reaction rate could be very, very slow, okay? Because of the different, let's say, phases of the reactants and products. You can have a solid and a gas that can react, but because a solid doesn't have the surface area that a gas has, the reaction is very slow. So we learned last year, what factors affect the rate of a reaction that can go? I didn't say that last year. Last year I said, what are the factors that affect the rate of reaction? Now I have to say, what are the factors that affect the rate of reaction that is spontaneous, right? Because if the reaction is not spontaneous, it doesn't matter what I do to try to help that along. So if a reaction has a delta G that's negative, what can I do to increase the rate? Remember, well, the first one, and there's many of them, of these factors that you should be aware of, but one of them, okay, is usually increasing temperature. If you increase the temperature, you're going to increase the rate at which molecules collide. And as we learned, rate law is about molecules essentially colliding. Okay, now there's two types, there's basically one collision we need, an effective collision. We need a collision that has the proper orientation in places where bonds can occur, and they have to have enough kinetic energy to overcome their repulsive forces. Temperature is a measure essentially tied to thermal energy. So higher temperature means that you've added more energy to the system and you've given the molecules more kinetic energy to collide more often. If they collide more often, the chances of an effective collision have increased. So temperature increases the rate of reaction. Okay, we know that. If you want to cook something faster, you increase the temperature. So we know factors that affect increasing the temperatures. What are the factors? Well, how about surface area? Okay, I did a demonstration last year where I lit some powder on a table. I took some toilet seat cover, wooden toilet seat covers, sawdust, if you remember, and I lit the sawdust. It burned. It wasn't a sexy demonstration. But then when I blew the sawdust as a fine powder over a flame, you saw this tremendous flamethrower. So if I increase the surface area, the availability for atoms to hit other atoms, you're going to have a higher rate of reaction. You're going to what? Maximize the ability of the spontaneous reaction by providing conditions that allow for molecules to collide with each other better. That's what the rate factors are. Something that is a delta G, it's negative. You're changing the conditions so that you're helping them achieve their potential in terms of that pathway. You're helping atoms collide with atoms, effective collisions. So surface area. Okay, now if you increase the surface area, atoms certainly will be able to find each other. Another one we talked about is increasing or changes of pressure. Now, if you increase the pressure of a gas and you have reactants that are a gas, you're pushing the molecules closer. By pushing them closer, they're going to collide with each other more often. Therefore, the frequency of collisions increases and the number of effective collisions increases and the rate of reaction goes up. Another factor, if you remember, is adding something called a catalyst. If you add a catalyst, we learned that a catalyst will lower the activation energy by finding an alternative pathway. It lowers the overall energy to start a reaction. We're going to learn about that, specifically what a catalyst does. Okay? But a catalyst also will help speed up a reaction, possibly helping the number of collisions or finding another pathway in the mechanism. It's a little bit different than these, but we'll talk about them and see that close hand. What other factors do we have besides that? We're missing a big one. Yes? Yeah, changing the concentration, and that's the one we're going to be focusing on. So the biggest factor that we're going to deal with is changing the concentration of the reactants, right? If you increase the amount of reactants, you provide for more opportunities for atoms to collide. So changing the concentration of the reactants, okay, is something that chemists spend a lot of time thinking about in terms of how fast they want their reaction to go. Yes, we do a lot of catalyst work. Okay, surface area and pressure, all those are important, but this is the number one way that we control for how fast a reaction goes in terms of industry. And that's what the rate law is built upon, the concentration of the reactants. Okay, now, as we go forward, let's talk about how we determine something called the rate law. We determine from it experimentally. Now, the rate law is a formula. That formula is something that I can use to figure out how fast, how much change of my product over time I get. All right, now we can only get from it, or get it, this rate law, this equation that helps me determine how fast something is experimentally. Because we can't see atoms collide, we can't assume a couple things. So before I get there, let's look at this very, very clearly. Let's look at it another way. So let's take a reaction. Let's say we have X plus Y making XY. Okay? I don't care what the atoms are. And of course, that means we have some X in the reaction vessel and we have Y in the reaction vessel. We'll draw a couple of them. Okay? And clearly they have to collide effectively in order to make XY. All right. So what we're trying to do here is figure out some kind of equation that's tied to the concentrations, or the initial concentrations of our reactants. So what we're doing is we're building this equation. And we can't do it just by looking at the coefficients. And there's a reason for that. Because we're looking at something called an elementary reaction. That's very important you understand that. I'm showing you something called an elementary reaction. When it's elementary, what I'm saying is one step. The process is one step. So we're going to assume in my examples right here that I'm dealing with one step elementary reactions. There's no other steps. I said, well, most people think that all chemical reactions are just one step. I give you the reactants and here's the products and we balance. But most reactions have a reaction mechanism. Case in point, here's a reaction between 2 NO2 that makes 2 NOs and an O2. Now, it is not an elementary step, meaning we think there's 2 possible ways this can happen. Example number 1 are proposed, and it's called a mechanism. Most reactions are not one step, and you can never assume they're one step by just looking at the reaction, because you may say 2 of these kind of hit each other, and when they hit each other, they make 2 of these and O2. That's what you're thinking if it's one step. But we know from experimental studies, we're going to talk about how we get that it's not one step, and I'll explain when we get to that point. Here is the first mechanism. NO2, the first step someone proposed, breaks apart into an NO and an oxygen. This oxygen, which is called an intermediate, immediately hits another NO2 and makes O2 and NO. And if you cancel out what's on both sides, which is the oxygen here, okay, you can clearly see that we get the overall. This is a 2-step process, okay? But as you can see, there are other proposed ways to do this. So what we're doing in rate law is we're trying to figure out and understand exactly how the reactions work. Knowing exactly how the reactions work and understanding their mechanisms is like almost, as some people say, playing God. Pharmaceuticals are made to jumpstart some of these. Now, I'm showing you very simple mechanisms. Some mechanisms are 20 pages long. And if you can understand how the reactions work and how the side reactions work, you can control very, very complex reactions by jumping into the mechanism. We'll talk more about that. But let's get back to elementary steps. An elementary step is a single process. This is an elementary step. This is an elementary step. Combined, they make the whole mechanism. Now, before we can get to understand which proposed mechanism may be the best, we need to think about what this means. Again, we're trying to build a formula called the rate law, and we need to understand from how the initial concentrations change to do that. So, here's what I'm going to do. If this was one step, okay, and I'm going to double X with respect to Y, keeping Y constant. By doubling X, what can you say about the number of collisions in the same time period? Assuming that Y is in close proximity, if I have this reaction, and having equal amounts of X and Y, I time the reaction. I time the reaction measuring what? Well, I measure the molarity per second. I may get some kind of number that tells me the molarity per second of what? The concentration of XY. Okay? Now I have that value for equal concentrations. Now I double X. What can you say about the rate now? If it is just one step, logically, doubling X, doesn't that double the opportunity for Y to collide with X? Of course. So the rate of this reaction does what? By doubling X and keeping Y constant. It doubles. So we say by doubling X, keeping Y constant, this rate, how fast I make, will double. And when you triple X, can you guess what's going to happen to the value of the rate law? As long as you have enough Y there. You're going to triple the rate. You quadruple X, you quadruple the rate. We would say with respect to X, we would call that first order. And our rate law would look like this. R, which is the rate, which is molarity per second, is equal to some constant we'll talk about. It's temperature dependent, okay, times the concentration, the initial concentration of X to the first power. We say that whatever I do to X, it does to the rate. I triple this to the first power, that means it's just whatever this is. I triple this. And you can understand that. Now this is only for this elementary step. What if I do the opposite? What if I do the opposite? So what if I come here and I erase these X's and I put some Y's here? Why? Because I want to. Now, keeping X constant, knowing what the rate is with these equal concentrations, and now I double y, can everyone see what's going to happen to the rate? Well, it should double because I'm providing twice as many y's in the same vicinity for the x's. So there's going to be twice the number of collisions. So what order do you think y is with respect to x? Y is also first order. Okay, what does that mean? Whatever you do to y, keeping x constant, you do to the rate. Now, what if I double both of them? If I double x and I double y from initial conditions, this was the initial condition, what do you think is going to happen to the rate? Well, that should be an x. If I double both, doesn't each one now have twice or four times, I'm sorry, have 4 times the opportunity to collide now? Yeah. So if I double x with respect to y, this one has twice, or this y has twice the ability to react. If I double this one with respect to this y has twice the ability. So you have an overall 4 times increase of the number of collisions in the same time period. Which, by the way, a 4 times increase of the rate, okay, when you multiply numbers that are exponents, what do you do to the exponents? You add. So we would say that this reaction is overall second order. So this is a second, this is important, second order reaction. What does that mean? Well, if I double both of these, my rate is going to change by the square of that, which means if this was 1 molar, now it's 2 molar, this rate now is going to be 4 times. Okay? So second order reactions tell me that essentially that my rate is going to be the square of the changes of my initial concentrations. Okay? Now let's do this again. Let's do another elementary step. All right? Let's do this. Let's change this up. We're going to do another one step. Now notice something, party people. Do you notice that this will always probably be the coefficients if it's just a single step? Yeah, theoretically. Let's see that. Let's say we have this reaction. Let's say we have, make things very simple, get rid of this y. Let's make it x go to x. Diatomic. So we have some x's. Okay. Now, I double the x concentration. Double the x concentration. Here are my initial conditions, and I double the x concentration. What's going to happen to the rate? It's going to increase 4 times. By doubling x, which is on both sides, the x's have 4 times the ability to collide. So because the rate is equal to what? The order, or the exponent, we would say with respect to x, what's the order here? Order would be 2. And if I redo this reaction, wouldn't this be 2x? Goes to x squared. And look at here. The coefficient is the exponent. There's a tie there. All right? So the coefficient is the exponent only if, though, I have a single step. So when I write a chemical reaction, how do I know it's a single step? I don't. I can't assume it is. I have to test. I have to take some conditions, change the reactions. I need an experiment. I can't assume. However, once I find my individual steps, I have my individual rate laws for these. And we're going to see that in a second. But let's do one more scenario that opens the door, the possibility for something called a mechanism. Okay, let's watch. Okay, let's take, now I'm going to give you something called a mechanism. All right? It's no longer going to be one step. There's going to be a bunch of elementary steps. So here, let's say I have x plus z, and that gives me xz. Okay? Xz plus y gives me xy. And if I cancel all things that are on both sides, I'm going to cancel this guy. Oh, I'm sorry, I forgot one thing. Plus z. Let's get rid of this. Now, notice I did not give you one step. I gave you 2 elementary steps. Okay, now, the overall reaction is x plus y going to xy. Now, if you did not know this, you may assume, hey, that's easy. Hey, it's one of these and one of these, the rate law. Hey, is R is equal to the constant, temperature dependent, x to what order? First. Yeah, and why to the first? Because logically, if it's only one step, doubling this will make the reaction double. But how do I know it's not this? How do I know it's not 2 steps? Now watch, we don't know. That's why we need the experiment. Let's say we did the experiment and it showed the following. It showed that the K, okay, times, well, let's think about this. What's going on here? X and Z come together. Z is not part of the equation, but Z gets reproduced. What do we call that? What do we call this? Something that starts a mechanism. Mechanism is a bunch of steps. Without Z, this bunch of steps don't occur. We learned last year that a catalyst starts a whole new pathway. Z is a catalyst because it starts this set or chain of mechanism or individual elementary steps. So this is a catalyst. What do we know about catalysts from 6th grade? Catalysts are never what? Consumed in the reaction because they're what? Reproduced. So a catalyst starts a mechanism. So this is a catalyst, okay? Something like that. Oops. I don't know what just happened. So here's my catalyst. And what is this? That is called an intermediate. You notice it's not, neither one is part of the equation because they get canceled. An intermediate links one step to another. Normally intermediates are unstable compounds. They don't last very long. Okay? So this first step, okay, you think about it, sometimes this first step is very fast, but making intermediate means as soon as you make this is going to go. So that means the first step, when you're making intermediate, generally speaking, has a slow rate of reaction. So this is usually slower. Why? Because I'm waiting to make this. As soon as this is made, this is going to react. This is unstable, so it takes some time to make this, but all of a sudden, as soon as you make it highly reactive, think with me for a second. If I'm making a highly reactive intermediate that links this step to this step, this second step, okay, is going to go pretty darn fast, okay? But it has to wait for who? It has to wait for the first step. So this will be a fast second step. Why? Because the intermediate normally made are these things where you have reaction. We don't see them ever in the reaction container because they don't last long, but they connect one to the other. So this has to be the faster step because as soon as it's made, boom, it's waiting. But as we talked about last year, this whole process, the rate of this reaction, is dependent upon the slowest and weakest link. What are we waiting on? The first step or the second step? The first step. The slowest step because it's the one that everybody waits for. When I got to go somewhere in my family, my kids, I'm done. Okay, I put my hair products in, I perm my hair, I comb it. For whatever reason, it doesn't take me much long to get ready. Okay, I wear the same thing every day anyway, so who cares? Okay, my wife, we're waiting. So the faster we get somewhere, the rate determining step is my wife. I don't understand, but that's the way it goes. So as we want to go somewhere as a family, or these are some people, we have to wait for this step. So we call that step an important step called the rate determining step. Rate determining step. The slowest step. Which means what? I circled both of them. Okay, bad Grotsky. So what does that mean? It means the slowest step is number 1. It means that my rate law is dependent upon the first step. So this is my elementary step that the rate law depends upon. So R equals K, X to the what power? To the first. I can't put Z in here. Z is a what? It's not a reactant. It's about the reactants. I can't put intermediates in here. So I'm just left with Z, X to the 1. But I've got a Y here. Guess what? When I change the concentrations of Y in my experiment, remember, we don't know this. We have an experiment that told us this. When I increase the concentration of Y, it has, assuming there's X, there's no effect on the rate. When there's absolutely no effect, I double Y, keep X constant, the rate stays constant. What's the order for Y? 0. So you can write it here if you'd like, Y to the 0, but anything to the 0, of course, is 1. And you can see, experimentally, I found that when I double X, keep Y constant, the rate doubles. Hey, X to the 1. I double Y, keep X constant, no change. That tells me this is not a single step, and this is a possible mechanism. Y is not in the rate order because it's not in the rate determining step of my mechanism. You see, the experiment helps us with proposed mechanisms. All we know is we can't watch these things happen. We can propose the steps, and then we can test them to see if they make some sense. So this is a possible mechanism. This is a 2-step process, not a 1. If it was a 1 process, this would be what? R equals K to the 1 and Y to the 1 if it was a 1-step element. But because it goes to 0, it screams to me that this is not an elementary step because it's got to be in a multiple step process called a mechanism, and it must not be in the rate determining step. So when you have a mechanism and you know the slowest step, your rate law comes from that step, and if one of your reactants isn't in it, then it gets a 0. Now what if this was 2x plus y, and 1x was here and 1x was here? 2x would tell you, hey, that's squared. But if one of the x's is not in the rate determining step, it'll still be x to the 1. So the coefficients do not always equal the rate law. When they don't, they scream to us as chemists that we're dealing with a mechanism, a bunch of steps. And what we do is propose them and then test for them experimentally. Does that make sense? Okay? All right. So let's look at these 2 reactions. Let's go on to my site here, and let's go to the rate law, and let's look at these proposed mechanisms. All right, so here we go, party people. Reaction mechanisms. Okay, and here's the first proposed mechanism. And before we even do that, let's take a step back. There are a couple of different ways you can have 1-step processes, which means here's N2O4 by itself dissociating those 2 NO2 molecules. Remember those, I put them away, darn it. Remember those glass tubes that are brown gas and the clear gas? This is the clear gas, this is the brown gas. It's called unimolecular. This doesn't require a collision. This is kind of like giving off an alpha particle or radioactive decay. Unimolecular, okay? Bimolecular means you have 2 things. This is the most common of all reactions. So this is a first order reaction. You have an X waiting for something to happen. This is a second order reaction, 2 things. And this one, I'm not going to even write it. What are the chances of 3 things coming together at the same time? Small, so we don't even write it because we don't even think it exists. These are the 2 basic types of elementary steps. Okay, notice I don't have 3 things in each one of my elementary steps in my mechanism. Okay, so as we go forward here, possible mechanism 1. NO2 stretches, okay, and breaks apart to NO and NO. Again, we don't know. We're guessing this might happen. Okay, then we make what? NO and NO. O is the what? O is the catalyst. What is it? It's linking one elementary step to another. So what is O? It's an intermediate. Do you think that oxygen, elementary oxygen not bonded to itself, just O, is highly reactive? Is there oxygen other than O2 in our environment that's going to hang out? Isn't O2 stable? Is single O stable? No. What do we learn about atoms and heats of formation? Where's the baseline? The high energy are the what? The free atoms. This is highly reactive. It's not going to stay around. So this is, once it hits the NO2, okay, boom, this goes. Now think with me for a second. This is waiting for this to be produced. This goes fast because O is very highly reactive. So where's my slowest step? First one. So my rate law depends on the first step. So if this is the correct, okay, my rate law would be what? R equals what? If this is my slow step, which is the rate determining step, that means my rate law depends on this single elementary reaction. And we would write R, okay, R is equal to K times what? NO2 to the what power? 1, correct. Okay, that's mechanism 1. Again, those are just proposals. We go forward. Here's possible mechanism number 2, where we have an NO2 and 2 NO2s. Okay, so we have 2 of these. This was unimolecular. This is bimolecular. 2 NO2s colliding. What do we make? An NO3, which is our intermediate. Which is, guess what? Intermediates are highly reactive. So this is a fast step. So this must be a slow step again. If it's a slow step, that must mean that this is our rate determining step. What we get is R equals K to the NO2 to the second power. How can I find which is the best? I do an experiment where I do what? Keep double NO2. If the rate does what? Doubles, I know that this is the correct what? Rate law, which means that this is a better proposed. If I double NO2 and the rate squares, goes up increase 4 times, this is my proposed mechanism. So what we do is, we have to look and see. Okay? So, what do we find? Experimentally, we find that when we double NO2, we double R. Experimentally. And we find that this is the best proposed mechanism for the reaction. Only our evidence shows us that. Okay? So rate law is a way to look at initial reactions and figure out who is the best. How we can affect the rate law, or the rate of reaction by, okay, increases in initial concentrations. But it's so much more than that. By the rate law, we can determine, in fact, what is the best way the reaction proceeds. We don't see these things. I'm giving you simple ones. Okay, more advanced ones could be pages long, and we test for them by doing exactly what I say. But we cannot look at the reaction and say, oh, that's clearly second order. You don't know if it's a single process or it's these steps here. Okay, it just so happened that it did match this up. Okay, and that's how we go about doing this further. So this is the beginning intro. Now, a couple of things I want to talk about, and I will give you a little break before I continue, is if we go on a little bit and go back here, let's write this reaction. I want you to understand stoichiometrically. So what we had here in this reaction, we had NO2 and 2 of them, Okay, and the overall reaction was NO, 2 NOs, and an oxygen, O2. Now, here's some things you need to be careful of. There's some designation here. I can say the following different things here. I can say that with respect to O2, the change in the concentration of O2 over the change in time is equal to negative 1/2 the change in the concentration of NO2 over the change in time. What does that mean? This is the overall reaction. It's not the rate law. What I'm showing you is the stoichiometric coefficients are tied to each other. Okay, meaning, as I increase oxygen, why is it 1/2 that of NO2? Look at the order, look at the ratio. It's 2 to what? 1. So as fast as I create O2, I lose half as much NO2. It's a stoichiometric condition. So if I want you to relate, if I give you the rate, and I can give you the relationship to the losing of the reactants or gaining of products, you should be able to link. So if I know something is the following. If I knew that the rate of O2, if I knew the rate of Christmas in July, if I knew the rate of O2 is 4 molars per second, so let's do this. So if the rate for this reaction of development of O2 is equal to 4 molar per second for O2, what is the loss per second of NO2? If the production of O2 is 4 molar per second, what is the loss of NO2 per second? 2, because of the what? 2 to 1 ratio. All right, so I'm going to stop here. That's the introduction. I'm going to have you take a break, and then we're going to start looking at experimental evidence to get the orders of reaction for the overall equation and start thinking about what proposed mechanisms may exist.